We started this topic last week on statistical linear model. And of course, I remember we're trying to characterize relationship between variables, and I actually walk you through the model specification if we want to do that within statistical framework. And I remember I also walk you through what I call the method of estimating parameters in a linear model, which I call the method of least square. And I remember I walk you through, we started working on the properties of least square estimator. The last time we met, I show you that the least square estimators are unbiased. And of course, what we want to do today, because we got some materials to review today, this is going to be the outstanding from the materials on Monday. And that's why I want to start with that before moving to the material today. You know, the whole thing in statistics is more or less like a story. Okay, we have been investigating properties of a very good least square estimator, and we've talked about unbiasedness properly. We've already done that, and today I'm actually going to walk you through other properties like consistency and efficiency. Okay, now I want to, this is a consistency. Of course, you remember the other time when we're working with the estimator, I told you when we talk where an estimator is said to be consistent, if you know if we're able to find the limit of the variance, okay, as n tends to infinity, okay, the variance converges to zero if we're referring to unbiased estimator. And then when the variance converges to zero as n tends to infinity, the implication of that is that the estimator converges to the true value of parameter. I remember when I was walking you through convergence of sample mean to population mean. Now we're going to have the same thing when it comes to least square estimator. You remember the least square estimator. Okay, we talk about the beta naught curve, the beta naught curve, and the beta 1 curve. They are least square estimator. And if you take a look at what I'm trying to say here, of course, when n tends to infinity, okay, I want to be able to show that the beta naught curve converges to true values of a beta naught, and the beta 1 curve converges to the true values of a beta 1, and that is only possible when sample size is sufficiently large. Okay, but we're actually going to have an assumption here if I want to show you this. Now, I need you to pay attention to this guy. Okay, when you take a look at this guy, this is a sum of square deviation around the predator, okay, around the explanatory variable S. I want to say it is mathematically proved and statistically observed that when sample size is large, this guy is going to tend to infinity. Okay, I just wanted to take note of that. Now, let us now see. So what I want to show is that the least square estimator, beta naught and beta naught cap and beta 1 cap actually converges to their true value. Okay, you know, when you take a look at the P here, that's a convergence in probability. Okay, now we want to show that now. So take a look at this. So the proof is, if we want to show that the least square estimator converges to the true value of the parameter, then as n tends to infinity, we expect their variance, their respective variance to converge to zero. Of course, the other time we derive their variances, right? Okay, we're going to make use of the formula for their variances. So we want to investigate that. Okay. I need you to pay attention to this guy now. Okay. Take a look at this guy. Okay. That was the variance of a beta 1 cap. We derived this before. Okay. Sigma square over SSS. And the SSS is the SSS is actually the sum of square deviations around the predictor X, so which is a summation, okay, X minus X bar, okay, all squared. Okay, now let's take a look at that. I told you the other time, when S tends to infinity, okay, that guy tends to infinity as well. And that guy is occupying denominator position. What is going to happen to the variance? The variance is going to tend to 0. That's exactly what we mean. And when the variance of an estimator converges to 0, when S tends to infinity, that shows that estimator converges to the true value of parameter. Now, that is how to show for beta 1 cap as an estimator. How do we show for beta naught? If I want to show for beta naught, I need to remember the formula for beta naught. We take a look at that. The formula for beta naught that we derive as this guy and n, and they are both occupying denominator position. When n tends to infinity, of course, we expect the whole of this. In fact, this tends to infinity, this also tends to infinity. They are all going, the whole thing is going to converges to 0. And when that happens, then we actually say the beta naught cap actually converges to the true value. Now, if that happen now, okay, but there's something I'm going to tell you. When an estimator is consistent, that doesn't mean it's going to be efficient. I'm going to say that again. Consistency does not imply efficiency. And the most important property of an estimator is efficiency, not even consistency. Because we're talking about consistency, of an estimator when the sample size is extremely large. In a research world, we may not have a sample size that goes indefinitely. Does that make sense to you now? And the reason why consistency does not translate into efficiency. I don't know whether you've heard about one of the, if I'm working with multiple linear regression, there's we normally have assumptions. Let me use this opportunity to discuss with you assumptions using this linear model. Okay, I think I've talked about number one assumption, talk about linearity. Okay, and linearity is if this guy equal to expected value of error equal to 0. Okay, and number two assumption talk about normality. Okay, normality, we try to talk about error follows normal distribution with mean 0 and variance sigma squared. Now, situation where we got so many variables, okay, there's no multicollinearity. Has anybody heard about multicollinearity? Has anybody heard about multicollinearity? Multicollinearity is a very serious problem in statistical modeling if relationship exists among explanatory variables. We don't want that. We only want relationship between the response and the explanatory variables. We don't want a situation where relationship exists among explanatory variables. When relationship exists among explanatory variables, the linear estimator will still be consistent, but they will no longer be efficient because multicollinearity diminish efficiency. Does that make sense? Now, what do I mean by efficiency in the first place? Efficiency actually means, how well an estimator utilizes information, okay, in the data, okay, that can be used to estimate the parameter. Okay, how well, a particular estimator utilizes that information, because we believe there's information in the data. And, an estimator will be more efficient if that estimator can fully utilize information in the data. And if I want to investigate efficiency, it depends on certain assumptions. It depends on distributional assumption. And not only that, it depends on whatever optimality criteria you are using. Okay. And if you want to look at the efficiency, you are comparing estimator with the you're comparing maybe among estimators. For instance, estimators may be consistent, but which one is more efficient? So I just told you now, consistency does not translate into efficiency, because consistency has to do with just minimizing the sum of square error. Minimizing sum of square error does not translate to minimizing covariance or correlation structure of the explanatory variable. Does that make sense? Okay, now we got a model specification that actually come with the error. The way linear regression model is going to come, and that's going to come with assumption. The error behaves well. Error behaves well when assumptions, because assumptions in linear regression centered around error. When those assumptions hold, then error behaves well. Okay, that's what we mean. Now, and we have another assumption, in addition to this, okay, because beta naught cap and beta 1 cap are random variable. I'm talking about the beta naught cap and beta 1 cap are random variable. Okay, then we expect them to follow normal distribution. Not only error, we expect error to follow normal, right? We also expect beta naught cap and beta 1 cap to follow normal distribution. Now, you know what I'm trying to say here. Okay, I'm looking at it in a bivariate case. Beta naught follow normal distribution with the mean of beta naught. What I say with the mean of beta naught, because the beta naught cap is unbiased. So expected value of beta naught cap is the mean of beta naught cap. So the mean of beta naught cap will give you beta naught. Then the mean of beta 1 cap will give you beta 1. Then what is this guy then? That guy is actually going to be called a variance covariance matrix. Don't forget I have two random variables. The variance covariance matrix, we are here, I'm actually going to have this 1 is going to be the variance of beta naught. Then I'm talking about the diagonal element now. Then that guy 2 is going to be called the variance of beta 1. So take a look at this. This is the variance of beta naught cap. This is the variance of beta 1 cap. Why in the off diagonal? That will be covariance. You remember the other time we derived the variance of beta naught cap, we derive the variance of beta 1 cap, we also derive the covariance. So this guy here, okay, that guy 1, 2 is also going to be the same thing as 2, 1. Okay, that's what we call covariance. The covariance of beta naught, beta 1 is the same thing as covariance of beta 1, beta naught. So that's what we mean. Okay. Now, another thing I'm going to talk about is, I walk you through how to derive the least square estimator. Okay. Do you know we can also use the method of maximum likelihood? Okay. But let me tell you this. The least square estimator will be equal to maximum likelihood estimator. I'm actually going to show you, I'm going to give you a clue how you can apply the method of maximum likelihood. Okay. Now, if then the number 3, I'm also going to show you how the sample variance is independent of these two. sample variance independent of these two actually means I can estimate sample variance on its own. Does that make sense? Now, I need you to pay attention now. What we're doing lately, okay, en route to the final. I know it's going to be complicated, but you know what? The moment you listen, the moment you stay focused, the moment you ask questions, if you don't understand, you're actually going to be fine. Okay? Now, you know what I want to do now? I need you to pay attention. What if I ask you to derive the maximum using the method of maximum likelihood to derive beta naught cap and the beta 1 cap? The method we used the other time was called the method of least square. Okay, but right now, we don't want to use the method of least square. In the method of least square, we minimize sum of square error. But in the method of maximum likelihood, we are actually seeking the optimal values of beta naught and beta 1 that will maximize the likelihood. Now, if you want to know, of course, it means I'm actually, I need a functional form. Okay. Now, that functional form that I need is going to be a normal distribution because we have an assumption of normality on the error. Okay. We have an assumption of normality of the error. Now, if you take a look at, so you're going to take a look at this guy now. Please, I need you to pay attention. You know, I want to talk about normal, right? Normal distribution is f of y equal 1 over square root of 2 of this y minus mu all squared. Okay, if this is f of y, okay, now what is mu? Okay, mu is actually expectation of y, which is beta naught plus beta 1s. So wherever I see mu in the normal architecture, I'm actually going to plug in that. Okay, so this guy is now going to become f of y, okay, given, okay, beta naught, beta 1, and sigma. Okay, now I'm actually going to have 1 over square root of 2 pi sigma squared exponential raised to power this y minus, then I'm putting this guy beta naught plus beta 1x all squared. You see now? Now, if I have this guy now, the only thing I need to do is to find the likelihood. Just, so the likelihood of y given this and this now, okay, is actually to introduce, I start from 1 to that, okay? If you simplify that, okay, 2 pi sigma square raised to power minus half exponential raised to power that y minus that, okay? Now, when you take a look at this now, okay, when you take a look at this now, okay, you now go back to the approach of maximum likelihood where number one, I'm actually going to, this is going to be raised to power minus n over 2, and this is going to be total summation here. Then I'm going to introduce a log, natural log to both sides. When I introduce natural log to both sides, you know what I'm going to do? I'm actually going to perform two derivatives. Number one, I'm going to differentiate. Now take a look at what I'm doing here. This where you see now, that's a likelihood function of a normal distribution after replacing the mean with a beta naught plus beta 1s. Okay, now this is now the maximum likelihood. Now, this is a maximum, I'm sorry, that is a likelihood function of a normal distribution after incorporating the model. Okay, what am I going to do to that? Then I'm going to introduce the log. Okay, introducing the log. Okay, we are back at method of maximum likelihood. This is going to be the log of the likelihood. If this is the log of the likelihood, you know what you're going to do? Differentiate this guy with respect to beta naught, equate it to 0, solve for beta naught. That will give you the expression for beta naught. Differentiate, come back to here again, differentiate with respect to beta 1. Okay, set it to 0, solve for beta 1, you will automatically, you're going to obtain the same expression that you obtain under the least square. And that was the reason why. Take a look at this scenario here. Take a look at this. That was why I said, take a look at that. I said, maximizing the log of likelihood with respect to beta naught and beta 1 is equivalent to minimizing the sum of square error with respect to beta naught and beta 1. When you are minimizing the sum of square error with respect to beta naught and beta 1, you are using the method of least square. When you are maximizing the likelihood with the respect to beta naught and beta 1, okay, you are actually using the method of maximum likelihood. Okay, in one, you are minimizing the least squared, the sum of square error. In another one, you are maximizing the values of, the likelihood. Okay, whether, minimizing, maximizing is an optimization technique. So take a look at that. And I said here, at the end of the day, you're actually going to get the same results for that, but not all the time that we're going to get the same result for other modules. I'm talking about linear module now. For linear module, okay, maximum likelihood and method of least square will give the same expression for beta naught and the beta 1. Okay. Do you know another thing I can do? There are three parameters here, not only beta naught and beta 1. I can also get the maximum likelihood for standard deviation or for variance. What I'm going to do is to go back and differentiate with respect to that. That is what I'm doing here. What am I doing? I'm differentiating with respect to sigma squared. Where am I differentiating with respect to sigma squared? Because I want to obtain the maximum likelihood of sigma squared. The maximum likelihood of sigma squared will eventually give us this. Will eventually give us that. And if you notice what we've done before, along the line, when you are minimizing or maximizing the beta naught and the beta 1, you're going to put a cap on them. Okay. Now I need you to pay attention to this guy. What is this guy here? Okay. If I want to write the odd thing here, is y minus y cap, right? Right? Y minus y cap, because the y cap is beta naught cap plus beta 1 cap s, which is sum of square error, which means the estimate of the variance using the maximum likelihood approach will give you sum of square error over n. But is that what we got when we use a least squared? When we use a least square, we got sum of square error over n minus 2. Do you remember? You can check your note. Because of that, then I'm actually going to say maximum likelihood estimator for variance is bias A, but the least square estimator for that is unbiased. Does that make sense? Please take note of that. Now, what I want to do now, I need you to pay extra attention. You know what I want to do? I actually want to show that sample variance is independent of the two estimators. Of course, it's going to be independent because when when you take a look at the maximum, when you take a look at the likelihood function has three parameters: beta naught, beta 1, and that. And if I want to obtain the maximum likelihood for each of them, I will need to go to the likelihood function one at a time. I will differentiate with respect to beta naught, set to 0, solve for beta naught, differentiate with respect to beta 1, set the resulting expression to 0, solve for beta 1, then differentiating with respect to sigma squared. Okay. Now I want to tell the world here, I want to show the world that the estimate that the sample variance is independent of the estimator. If I want to do that, this is what I'm first going to do. Take a look at this. If you really want to show that there are two variables are independent in statistics, then you need to show that their covariance equal to 0. If you're able to show that their covariance equal to 0, then you've been able to show that they are independent. Now, what I want to start with now, I want to start with what is y minus y cap. I want to first of all start with, is there a relationship between error? Because y minus y cap is an error. Is there a relationship between error and slope and the estimator for slope? Okay, if that is equal to 0, then that is going to take me to somewhere. Now let's take a look at that. Now, and from there now, we're going to get ourselves here because you know why? Take a look at this guy here. We want to, in the left-hand side, okay, if you take a look at this guy, that is y, right? That is y cap. Y, okay, when you talk about y, actual y, there's going to be error inside, actual y. But y cap is a predicted. The error is assumed to be 0 on average. And that was why you can see the difference between the two. Okay. Now, and of course, we still have the beta 1 cap. So what I just substituted is just y and y cap minus. Now, the next thing we actually is going to take us to take a look at this. I need you to pay attention. Comma, beta 1 cap, right? Error and beta 1 cap coming together. Beta naught cap and that one coming together. Then what do we have left? Beta 1, there's a beta 1 here, right? And X, right? We're also going to marry that with this guy. We're crossing them. And that will actually lead us to, that will lead us to this. Is there any question? Now look at the way we do that. Okay, the whole of this is an entity. Don't forget something minus y cap. Go ahead. Actually, what we're just doing is just like it's just like we have this. It's just mathematics. It's just like we have a plus 3 and 5, and we're now distributing like 5a, 5 and 5, stuff like that. That's exactly what we're doing here. Now, but don't forget, the whole thing is still gonna be co, because that's covariance, right? Now, the next thing now is, let's take a look at them one by one. Okay. I wanted to take a look. This guy is still this guy, right? This guy is still this guy. Okay. But you know what? When it comes to this guy, okay, when I have a covariance of the same thing, it becomes a variance. Just like what you said, covariance of me and me is variance. That means I'm no longer talking about covariation. I'm talking about variation within me. So because of that, this guy actually become a variance of beta 1. Okay. Now, when that guy become the variance of beta 1, what do I need to do next? Now, I want to work on this. Now, take a look at these 3 now. Okay. I want to work on them one by one. How many times? We got 3, right? Now, I first want to focus. I want to focus on this guy first. Okay. Focusing on this guy, I find myself here now. I'm still coming back to the other 2. Now, focusing on this guy, error. Then don't forget, I will, this is for this. Then this is the whole of this. You remember the beta 1 curve we derive from day 1. Okay. Now, when we have that guy now, you remember we made an assumption that this guy is the same thing as this. You remember? We made an assumption getting to that junction now. Okay. Now, the next thing that we're now going to have is this. When you take a look at, we find ourselves here now, right? How do we now? Oh, give me 1 second. I'm going to. Okay, so we find ourselves, this is where we are now. Okay, you know what is going to happen? What is going to happen is that if I have the covariance, okay, of EI and all of that, okay, what is going to happen? The covariance, the only variable here is Y, I told you. The covariance of Y is the same thing as variance of Y. And what is variance of Y? Sigma squared. Okay. Now, if that is sigma squared, what we're actually going to have inside is just going to be this guy. You know why? Because the error here, okay, the error here is a constant. And this is more or less going to be just the variance of this, where this is going to be knockoff. Okay. At the end of the day, we have that. And if we have that, we find ourselves here now. Okay. Now, when we find ourselves here now, finally, we're actually going to say we've gotten the covariance of E and BI. Now, the next thing is, we simplify this, and this is what we got for that. Now we want to simplify this guy now. Beta not cap and beta one. Beta not cap and beta one. Okay. And we've derived this before, if you remember. We've derived the covariance between the two before. I remember I told you this covariance will be 0 if x bar equal to 0. You remember? Now we've derived that before. And the third one, we know the third one here. We've derived that before as well, the variance of beta 1 cap. Now let us plug them in. Okay, so what we want to do now, we want to plug them into here. We want to put the expression for this, which is this. We want to put the expression for this, okay, which is that, which is this one. And we want to put the expression for this, which is this. And that's exactly what we put, okay, to be able to arrive at this. At the end of the day, by the time you plug all of them in, it's going to give you 0. You need to spend a lot of time on that. And when that gives you 0, by normality, implies error. Okay, error is the distance between y and y cap is independent of beta 1. The error is in the, what is the meaning of that? Error independent of beta 1? Oh, it means, error is any other factor that could affect in the response that we don't talk about. Okay, why is it that we don't talk about them? Because we believe their effect is very small, and that was why we said this. You know what I mean? On average, okay, their effect is very small, and that's why we don't include them in our model. There shouldn't be relationship between error and the slope. That is what we mean by independent. Okay. Now, lastly, so now, then, we've been able to show this is what happened. To be able to show this, okay, you need to for force show that relationship between the covariance between error and beta 1 cap equal to 0. We're also going to show that relationship between error and beta naught cap also equal to 0, because this is what we want to show. This is what we want to show. We want to show that variance is independent of beta naught cap and beta 1 cap. The very first thing we need to show is that the covariance between error and beta 1 cap has to be 0. We also need to show the covariance between error and beta naught cap also equal to 0. That is what we now want to show now, which is, we want to show this now. If we're able to show this and that, then we're going to make a conclusion. Now, take a look at it just like what we did before. If we follow what we did before, we're going to end up in that covariance equal to 0. You follow it up, and by normality, we're also going to conclude that the error is independent of beta naught cap. Now, the combination of the two, if the two hold now, take a look at the two here. When error is independent of beta naught cap, error independent of beta 1 cap, then we can make a conclusion that, the error here is independent of both. And that is also telling us if error is independent of both, don't forget variance that we're going to compute has to do with error as well. Okay, that's how we do that. I want to spend the next minutes on the other material. Is there any question moving forward? Yeah. Yeah, actually, there's a connection between this. What is this? No, it's an error, right? Okay, what do we want to prove? We want to prove that estimate of variance is independent of that. And what is variance? The variance is a function of this, because the estimate of variance, sum of square error divided by n minus 2. Do you remember that? What is the sum of square error? This is going to be y minus y cap squared, sum of that divided by n minus 2. I've answered your question, right? Okay. Now I want